Welcome back, everyone. Today we are going to start chapter 11, and we're going to start off with inverse variations. An inverse variation is a type of relationship between variables, and we'll get into how it relates to something we've seen before, which is direct variation. Let's get started. So inverse variation can be represented by the equation y is equal to k over x, or xy is equal to k. Now, the way these two equations go back and forth is that if you take x times y is equal to k, and if I wanted to rewrite this so y was by itself, well, I would divide by x to both sides, and now I have y is equal to k over x. So really, these two equations right here are kind of the same thing, but they show us different pieces. Okay, this first one talks about y. This second one talks about k. And we'll be using both of them, well, pretty equally this PowerPoint. Now, in an inverse variation, the product of the two values remains constant, aka k should always be the same regardless of what x and y values you multiply together. Now, a previous relationship that we've gone over is called direct variation, which is in the form of y is equal to kx. And if this sounds familiar, it should. Take the equation y is equal to 2 times x. Okay, this is an example of a direct variation, and it's also an example of a linear function. So if we were to create a table, and I was to say, 0, well, if I plug 0 in for x, y would also be 0. If I plugged 1 in for x, y would be 2. 2, 4, 3, 6. Now, in a direct variation graph, both sides of this table are going to increase by either addition or subtraction at a constant rate. So this one was plus 1. This is plus 1 as well, and plus 1. Plus 2. Plus 2, plus 2. And of course, here's where our 2 comes from. So both sides of my table increased constantly with addition and subtraction. In this case, it's addition, which means this is a direct variation. Okay? Inverse variation is slightly different because it is multiplication. Okay? X times y is going to be equal to k. Let's try this out. So here I have two tables. Now again, I'm going off of the equation x times y is equal to k. So if it's an inverse variation, when I multiply my x coordinate times my y coordinate, I should get the same thing. So in this one, this table A, I have 1 times 16. Well, that's equal to 16. Then I have 2 times 8, also equal to 16. And then I have 4 times 4, also 16. So this would be an inverse variation in which k is equal to 16. Now let's try table letter B. Okay, I got 1 times 3 is equal to 3. And then I got 2 times 6 is equal to 12. And immediately it fails. So it's not an inverse. Let's check and see if it's a direct variation. So, adding to the other side, so this is going to be plus 1, plus 1, plus 3, plus 3, and it is a direct variation. And in this slide, it just shows us the exact same thing. The first one was an indirect variation, or an inverse, sorry. My apologies if I've been saying indirect. It is an inverse variation, whereas this other one is a direct variation. And this would be the equation for the direct variation part. Whereas up here, since k was equal to 16, the equation for this one would be y is equal to 16 over x. And I got this equation from the pattern, y is equal to k over x. All I did was plug in for k. Now let's practice with the equations, because we need to be able to recognize this from either a table or the equation, because eventually we're going to get to graphing. We need to know how these concepts relate to each other regardless of their form. So, one more time, I have two different patterns. I have, for inverse variation, I have y is equal to k over x. And for direct variation, I have y is equal to k times x. So, with my equations c and d over here, I'm going to rewrite both of them so that they are both equal to y. And then I'll see which one is which. So this first one, I'm going to divide by 2 to both sides, which means I have y is equal to x over 2. Now, x over 2, this expression can be rewritten as y is equal to 1/2 times x. And this distinction is important because it fits our direct variation pattern. Over here, we have that y is equal to k times x, and then equation c can be rewritten in a way where we have a fraction, yes, but still a number, times x. So this top one is a direct variation. All right, let's check out equation D. So I need to get y by itself. I'm going to divide both by 2x. That gives me y is equal to 10 over 2x. Simplify. This gives me a 5 on top. So that means y is equal to 5 over x. Okay, 5 over x. This fits our inverse variation pattern exactly. A number divided by x is what we have. So this is going to be an inverse variation. Now let's figure out how to find k if we're just given points for x and y. So that first part was given the table, find k. Then it was given the equation, rewrite and determine which variation it is. Now we're going to assume that it has an inverse relationship, and we're going to find k this way. Again, we're just getting used to our pieces right now. We're eventually going to start graphing, and then it'll be really helpful to know where these concepts even came from. So, if x is 2 and y is 18, then they form the point 2, 18. And just like in the table, when we're looking to see whether it was inverse or direct variation, we're going to multiply these two coordinates together and see what we get. So I've got 2 times 18, and this is going to equal 36. So k is equal to 36. And if I were to write an equation of this inverse variation, it would be y is equal to 36 over x. Which means that this is my answer right here. So I found k by multiplying the coordinates together, and then it's a simple matter of plugging it into our formula. Let's talk a little bit more about, now last little bit, let's talk about what happens if we have 2 points, or more accurately, 1.5 points. So think back to that very first problem we did with the table, where we multiplied our coordinates together. Okay, now we're doing a very similar thing. So in this instance, problems like this would be, say you have 3, 5, and negative 2y. Okay, I have no idea if these numbers will work, but it's okay. So if we have 1.5 points here, one of the questions we could answer is that, if we assume this is an inverse variation, we can set up a proportion like this to figure out what our missing value would be. So then I would make this x1, this would be y1, x2, y2, and I would fit it into either this equation or this equation. It doesn't really matter which one. You're going to get the same answer, whichever you choose. I'm going to do this first one. So it would be 3 times 5 is equal to a negative 2 times y. And now you have an equation that you could solve for y with. Now again, I don't know if these numbers would work. I think we get a fraction. But let's go ahead and do a problem that I know will work. All right, here we go. Now, we're going to assume that y varies inversely, aka inverse functions. Okay, y is 3, x is 12. This is our first point. So that means I have 12 comma 3 is my first point. I need to find x when y is 4. This is my second point. Okay, so now that I have my 2 points, I can go ahead and label them. x1, y1, x2, y2, and can plug them into my pattern over here to figure out what my missing coordinate is. So 12 times 3 is equal to 4x, and then you can solve. And there we have it. 9 is equal to x, and that was what we were looking for. Okay, now that we've discussed our pieces, let's go ahead and try to graph. First things first, we need to write an equation. We need to write the inverse equation, and again, it's going to go off the pattern of y is equal to k over x. Now, since this is an inverse variation, it's not going to give us a straight line like the direct variation would. So it's going to look a little different, but it all makes sense. So let's find out, first off, what k is. So y is 8, x is 3. That's going to be 3 times 8 is equal to 24. So k is equal to 24, which means my equation is y is equal to 24 over x. Okay, now pause here. The go-to method whenever you don't know what to do when you're graphing is to create a table. Okay, pick x's, plug them in, see what the y is, plot the points. That's one of the best and most tried and true ways to graph anything. So as I'm looking at this equation, I'm thinking to myself, what x's should I pick? Because I can pick whatever x I want. And as I'm looking at this, I can think that 24 over x. Well, if I were to plug 5 in for x, that wouldn't work very well. 24 wouldn't divide nicely with 5. So I'm going to pick numbers on purpose that will work well and divide with 24 nicely. Okay, and for this I have 1, that goes into 24, 2, 3, 4, no 5s, 6, no 7s, 8s, that's about it. Or at least that'll do me all right because I only have a 10 by 10 graph right here. So I'm going to stick with those values for right now. All right, let's do my equation, and I'm going to do my negative values first. I'm going to start off small on my x's, and I'll explain why in a moment. So I'm going to say negative 8 for my x. So if I were to take negative 8 and I were to plug it in, that's 24 divided by a negative 8, and that would give me a negative 3. Okay, so then I got negative 6. If I plug that in, I would get a negative 4 out. If I were to go down my list again, I got negative 4. This would give me a negative 6. And then a negative 3. Well, that would give me a negative 8. Okay, and again, all I did was take my x values that I knew would work and plugged it into my y table. Or plugged it into my equation. Now let's do the positive side of these y values. Okay, let's start off with 1. Actually, no, let's go with 2. So if I were to plug 2 in, well, that would give me a positive 12. 3 would give me a positive 8. 4 to 6. 6 to 4. 8 to 3. And that should do it for right now. Okay, now let's plot the points. So my negatives first. Negative 1, 2, 3, 4, 5. Okay, oops. Sorry, changing colors. 5, 6, 7, 8. and then down 1, 2, 3. So here's my first coordinate. I'm just going to keep doing that. So over 6, down 4, over 4, down 6, and then over 3, 1, 2, 3, down 8. Okay, and if you want, you can add another point, -2. That give me a -12, and that would put my last value somewhere about right here. Okay, and so you can see the beginnings of this downward curve shape. But wait, we're not done. Now we have to do our positive values. And maybe, maybe not. You can see where we're going with this. So I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Just get a good scale going. And let's graph our positive points. So I've got 2 all the way up again to 12. So about right there. Okay, then I've got 3 to 8. 5, 6, 7, 8. 4 to 6. 4, 6. 6, 4. And then 8, 3. And just like with the other curve, you can see a downward curve-ish shape right there. And this is the graph of our inverse variation. These kinds of graphs have two big defining features. Number one is you have those double curves. Okay? Those are actually called hyperbola, and you need both of them. Okay? You can't just have the -1 or the +1. You have to have both to have the full graph. And then the other thing that's distinct about these kinds of graphs is you have this line that the graphs approach but never actually cross. And maybe or maybe not, you remember there's a vocab word that goes to these words. It is called the asymptote. Okay, so let's move forward. When we have direct and indirect variations, the direct or inverse variations, direct variation gives us a line that we're very familiar with, very comfortable with. Inverse variation gives us these hyperbola graphs. Okay, so as you see in this first one, if k is positive, you're going to have a graph like we had on the last slide. If k is negative, you can see how the curves kind of swap coordinates there. All right, now in the next lesson, we're going to go into a little bit more about these graphs and just getting comfortable with the graphs themselves. That's it for this video, though. If you have any questions, write them down, and I'll see you next time.